Hi everyone, welcome to my YouTube channel. My name is Jackie and I'm a graduated in electronic engineering from the University of Surrey. In this video, I'm going to share my project called Simple Cooling System on FPGA. If you are a beginner or interested in learning how to program an FPGA board using VHDL in Vivado software, you are very welcome to watch this video. This video focuses more on explaining the overall concept and showing the final result rather than diving deep into the code. This project demonstrates how I stimulated a cooling system using a finite state machine or FSM with 4 states: ideal, COOLON, ACNOWREADY, and ACDONE. In simple terms, we change the input signals to trigger different states, and each state will produce a different output. The FPGA board I'm using is the Xilinx Artix-7 XC7A35T-2FGG484 version. It's a compact yet powerful board that includes 100 GPIO pins, a 50 mHz on-block clock, 2 user push buttons, 2 LEDs, HDMI output for connecting to a monitor, an Ethernet port, and USB UART interface for serial communication, and an SD card slot for storing files. All the project files, including the VHDL source code and HTC pin assignment file, are already available on my GitHub, which you can see in the video description below. Here you can see the Artix-7 FPGA chip at the center with HDMI output on the right, USB UART and JTAG ports for programming, and 2 user buttons and LEDs on the top. It's a great development board for beginners who want to start learning FPGA programming and VHDL design. In this video, we are only using some of the main features from the board for our hardware setup. The first components are the 2 on-board push buttons. Key 1 acts as the cool input and key 2 acts as the AC ready input. The second components are the 2 on-board LEDs. D6 is used to represent AC on, and D5 is used to represent fan on. These LEDs help show the output of the current state. In addition, we also connect 4 external LEDs, red, green, yellow, and blue, to clearly display which state the system is in. All of these LEDs are considered output from the Finite State Machine. The system also uses a 50 mHz on-block clock oscillator, which keeps track of the state transition. Don't worry if you are not familiar with how everything works yet. I will explain how the states change and how the LEDs respond in the next part. This slide shows the pin assignments for the project. You can pause the video or take a screenshot if you want to check the pins numbers carefully. These are basically the connection that tells the FPGA board which pins we are using for the buttons, LEDs, and clock. The datasheet link is provided in the video description below, so you can refer to it for more detailed information. I'm not going to too deep into the pin assignment here because we are only focused more on the system behavior and result later. Alright, so this is the hardware connection. You can pause the video again if you want to take a closer look. The wiring is mainly based on the pin assignment I showed earlier. I just connected everything according to the table. Before looking at the state diagram, let's first understand how the hardware design actually looks in VHDL. So here we are basically building a state machine circuit. At the very top level, or you can say the outer layer, we have the input ports and the output ports. The inputs are key 1, key 2, and the clock signal. The outputs are the 2 on-board LEDs, LEDs 1 and LED 2, plus the 4 external LEDs, red, green, yellow, and blue. Once you understand the ports, we can go deeper inside the FSM internal logic. Inside, you will see 2 internal signals, cool and AC ready, going into a combinational logic block. This block decides the next state based on the current inputs. Then, the next state is stored inside a D flip-flop, which updates only when the clock rises. The flip-flop output, called the current state, goes back to the combinational logic and also controls the outputs, AC on and fan on. These outputs finally light up the LEDs depending on which state the system is in. Alright, This page is very important. It shows the main idea of my state diagram design. You can pause the video or take a screenshot if you want to look at it more carefully. So at the start, we are in the ideal state, both on broad LEDs, LEDs 1 and LED 2 are off, and only the external red LED is on. To move to the next state, called the COOLON, we need to change the inputs. That means pressing the key 1 button, which sets cool equal to 1. Now, we enter the COOLON state. In this state, LED 1 turns on, meaning AC on is active, while LED 2 stays off, and the external LED switches to green. After that, when we press the key 2 button to set AC ready equal to 1, we go to the AC now ready state. Here, both LED 1 and LED 2 are on, showing that both AC on and fan on are active. The external LEDs change to yellow. Then, when we press the key 1 button again, setting cool equal to 0, we move to the AC done state. In this state, LED 1 turns off, LED 2 stays on, and the external LEDs becomes blue. Finally, if we press K2 again to set AC ready equal to 0, the system goes back to the ideal state and the cycle repeats. Alright, so even though it looks simple, like you just press a button and the system magically changes the state and updates the LEDs, you might wonder how does it actually remember which state it's in. The real reason behind that is this small but super important component called the D-type flip-flop. The flip-flop job is to store the output, or what we call the current state, and it only updated the value on the rising edge of the clock. Now, what's a rising edge? The board had a 50 Mhz clock oscillator, which you can imagine as a digital wave quickly going from 0 to 1 to 0 to 1 over and over again. Because it's 50 MHz, one full cycle takes 20 nanoseconds. If we zoom in on that waveform, you can see when it goes from 0 up to 1, that moment is called the rising edge. And there are two simple rules to remember. First is, when it is in the rising edge, the output will follow the input at that instant. The second rule is, when it is not in the rising edge, the output stays the same no matter how the input change. Okay, let's take an example of how the system changes from the ideal state to the COOLON state. Remember, this process happened in two steps, step 1 and step 2. In the first step, we look at what happens during the first rising edge of the clock. At this moment, the flip-flop has an input called next state and an output called current state. When the clock just rises, the flip-flop updates. So right now, next state is equal to ideal, which means the current state is equal to ideal too. This value gets sent back to the combinational logic box, so it now knows that the current state is ideal. Now, at the same time, the user presses key 1, which makes cool equal to 1. The combinational logic calculates that based on this, current state equal to ideal and cool equal to 1. So the new next state is equal to COOLON. But remember, all of this happened at the same instant. While the combinational logic is still figuring out the new next state, the flip-flop is still seeing the old input, which was ideal. That's why the current state hasn't changed yet, it's still ideal. So right now, all LEDs stay off except the red LED, meaning the system is still in the ideal state. That's why we say at the first rising edge, the state has not changed to COOLON yet, it's still ideal. Alright, now let's move to step 2. This is the next rising edge of the clock, right after the first one we talked about just now. So at this new rising edge, the flip-flop updates again. Now the output or current state becomes equal to the input next state, which was already calculated earlier as COOLON. So now the current state equal to the COOLON, and the value got going back into the combinational logic, and the user still keep pressing the key 1 button, which means that the cool equal to 1. The combinational logic checks that and calculates again, but since we're already in COOLON and cool is still 1, the next state stays as COOLON, no change. At the same time, the flip-flop is seeing the same input from the last cycle, so the output remains stable. Now you can see on the output, the LEDs 1 turns on, which means the AC on is active and the green LED lights up to show the system is in the cool-on state. So basically, changing the state takes two rising edge, one to prepare the next state, and the next one is actually updated. That's why we call it a one-cycle delay between states. So yeah, in theory, we found that every state transition actually happens one clock cycle later, which means there's a small delay, but in reality, the clock is running at 50 MHz, which is super fast, so the delay is basically invisible to the human eyes. You won't notice any lag at all when the LEDs change. Alright, in this part, we are going to look at the real LED's output when we change the inputs to move between states. So first, when the code is running, the system runs in the ideal state. You can see both D5 and D6 LEDs are off, which means the air con and fan are both off. The external red LED is on, showing that we are in the ideal state. Now, if I press the K1 button, that's changed the cool signal to 1, which makes the system move to the cool on state. In this state, D6 turns on while D5 stays off, meaning AC on is equal to 1 and fan on equal to 0. You can also see the external LED has changed from red to green. So yeah, that's how we move from ideal to cool on just by pressing the key 1 button. Here's the video of me actually pressing the key 1 button, so you can see how the LEDs change in real time. Alright, now let's move to the next transition from cool on state to AC now ready state. Right now we are in the cool on state where D6 is on and D5 is off. That means the AC on equal to 1 and fan on equal to 0, and you can see the external LED is green. To move to the next state, I will press the K2 button, which set the AC ready equal to 1. Once that happens, the system jumps to the AC now ready state. In this state, both D6 and D5 are on, meaning both AC on and fan on are active. The external LEDs also change from green to yellow, showing that the system is now ready for air conditioning. And again, I will show you a quick real video clip of me pressing the K2 button so you can see how it changed from cool on to AC now ready in real time. Alright, now let's move from the AC now ready state to the AC done state. Right now we are in the AC now ready. Both D6 and D5 LEDs are on, which means both AC on and fan on are active. The external LED is yellow, showing that the system is currently ready. Now if I press the K1 button, that's changed cool from 1 back to 0. When that's happened, the system switches to the AC done state. In this state, D6 turns off and D5 stays on, meaning AC on equal to 0 and fan on equal to 1. The external LEDs also changed from yellow to blue, showing that the cooling process is done. And again, I will show you a short video clip of me pressing the K1 button so you can see how the LEDs changing from AC now ready to AC done. Alright, now for the final part, we are going back from the AC done state to the ideal state. Right now we are in the AC done state where D6 is off and D5 is on. That means AC on equal to 0 and fan on equal to 1. The external LED is blue, showing that the cooling process has finished. Now, if I press the K2 button, it's changed AC ready from 1 to 0, which brings the system back to the ideal state. Once it's switched back, you will see both D6 and D5 LEDs turn off, and the external LEDs change from blue to red, meaning we are back at the starting point, the ideal state. And in here, the real video clip showing me pressing the K2 button so you can see how it transitioned from AC done back to ideal. Alright, that's the end of this video. Thank you so much for watching. I hope this helped you understand a bit more about state machine design, especially if you are a beginner learning FPGA. If you found this video helpful, don't forget to like and subscribe to my channel for more FPGA and electronics projects. Thanks again for watching and see you in the next video.